In the 1990s, Singapore formulated the Deep Tunnel Sewerage System, DTSS, with the intention of implementing a sustainable and economical approach to managing the country's long-term requirements for used water collection, treatment, reclamation, and disposal. The project was divided into two phases and spanned over 2 decades. Phase 1 was concluded in 2008, and Phase 2 is projected to be finalized in 2025, as a result of infrastructure deterioration over time and the extensive land area that was utilized to house treatment plants and pumping stations. The DTSS was thus conceptualized in 1995. The DTSS project consisted of 4 primary elements: 2 deep tunnel sewers, 2 water reclamation plants, a network of linked sewers and deep-sea outfall pipes. Both deep tunnels span Singapore at depths of up to 55 meters underground and have diameters of up to 6 meters. The deeper tunnels are linked to the existing sewerage system through smaller linked sewers, which redirect used water flows from the existing sewers. Water is transported entirely by gravity to the 3 water reclamation plants situated in Kranji, Changi and Tuas via the deep tunnels. The new water factory was an element of the Changi water reclamation plants, which were able to treat 900,000 cubic meters of used water per day for additional purification and reuse. Phase 2 comprises a new wastewater treatment plant located at Tuas. By also integrating a new water factory and collaborating with the Integrated Waste Management Facility as part of the Tuas Nexus initiative, the upcoming Tuas water reclamation plants can treat about 800,000 cubic meters of used water daily, by means of biogas production and the co-digestion of food waste and sewage sludge. This collaborative endeavor optimizes the utilization of water, energy, and waste management resources at both establishments. The surplus electricity generated is also fed into the power grid. The Sirlitar, Burdock, and Kim Chuan wastewater treatment plants, in addition to the Serangoon sludge treatment plant, were gradually shut down following the completion of DTSS Phase 1 in 2008. As soon as operations for Phase 2 commence, the Ulu Pandan and Jurong water reclamation plants will be decommissioned as well. Using gravity, DTSS results in the elimination of the numerous pumping stations utilized in the conventional conveyance system. DTSS implementation will ultimately reduce by half the 300 hectares of land devoted to operational water infrastructure that existed in the 1990s. Thus far, this has been reduced to 190 hectares with the completion of Phase 1. The DTSS has enabled Singapore to maximize the utilization of land, which is limited for alternative developments. For example, Sirlitar Aerospace Park is currently occupying the space where the Sirlitar water reclamation plants once stood. Additionally, DTSS eliminates the risk of used water contaminating water catchments as a result of pumping station failures or main breakages. Consequently, intermediate pumping systems are no longer required. DTSS also obviates the necessity for heavy maintenance of pipes, resulting in cost savings. As a result of the inherent unpredictability of geological conditions, tunnel construction presents engineers with a complex challenge. Tunnel boring machines encounter a significant challenge in traversing diverse ground conditions, which comprise intricate geological formations, diverse rock types, and small fault lines. Engineering complexity is increased for the project due to the rapid and unpredictable changes in ground conditions. In order to tackle geological complexities, engineers employ a methodical and proactive strategy. Before tunneling operations commence, comprehensive site investigations are carried out through the strategic placement of boreholes to collect data on expected ground conditions. Difficult ground conditions may emerge despite exhaustive preparation, requiring periodic maintenance halts on the tunnel boring machines due to cutter blade abrasion. To comprehend prevailing conditions, validate the rock face that is being tunneled, and facilitate prompt adjustments to the tunneling strategy, engineers depend on real-time analysis of excavated rock samples. An additional noteworthy obstacle that arose throughout the DTSS's construction was unintentional drilling into the DTSS tunnel while conducting site investigation work for neighboring projects. Such incidents necessitated the development of a comprehensive strategy to mitigate the potential dangers associated with unintentional encroachment. Despite the relatively minor damage, to prevent disruptions to the DTSS project, a measure was adopted to enhance site safety. Developers were required to geotag their drilling rigs. This geotagging ensures precise location tracking, and an automated alarm system is activated in the event of drilling in proximity to the pub's DTSS project. By means of this cutting-edge technology, timely alerts are generated to avert inadvertent drilling into vital infrastructure, thereby preserving the integrity of the DTSS construction. Powering the DTSS with renewable energy sources like solar or wind power could further reduce its environmental footprint. DTSS can generate energy by using technology like hydropower to create electricity. Its water capacity can also be used for cooling data centers. The DTSS highlights Singapore's integrated master planning capabilities to sustainably meet water management needs while unlocking social, economic, cultural, and environmental benefits.